Hello everyone and welcome to the coronavirus edition of the 11th lecture from our signal theory class. In this lecture you will learn about linearization, which is a way how we sometimes deal with nonlinear systems. But before we get to the linearization itself, we will first review the definition of the linear time invariant systems and explain why we care so much about this linearity thing. First, the review. From lecture 1, a system is time invariant if it does not change its properties in time. That is, if an input u of t will create the output y of t, then the system is time invariant when a time-shifted input u of t plus tau creates the output which is the same as before, except time-shifted by the same amount as the input. If this does not hold, a system is called time variant. Again from lecture 1, the linearity is defined in this way. We have a system that responds to an input u1 with an output y1 and to an input u2 with an output y2. Now the system will be linear if when I feed it this linear combination of these inputs, the output will be the same linear combination of these outputs. If this does not hold, the system is called nonlinear. Now, there are not that many operations that can be used to create linear systems. Here you have them listed. Derivative and integrations are linear. For example, a system described by this equation would be linear, or a system described by this equation is linear. Addition of signals is linear. For example, a system described by equation where you add these signals and their derivatives will be linear. This goes only for signals though. Addition of a constant is actually not a linear operation. If you added a constant here, the system would no longer be linear. Multiplication by a function of time is linear. This is an example of what I mean. U of t is the input, y of t is the output, and here I have a function of time which multiplies one of the signals. This system is linear, even though it is definitely not time invariant. And note that a constant is just a constant function of time, so multiplication by a constant is also linear. And also time delay. If you delay one of your signals, your system will be linear. If a system is described by an equation built with these operations, it will be linear, save for one caveat regarding the initial conditions which I will address in a moment. Here you have some examples of equations you can build with these operations. Ordinary differential equations with constant coefficients are linear, even though we will add some limiting rule about the initial conditions. The linear convolution is surprisingly linear. The Laplace transform and the z-transform are linear. When I'm given an equation describing a system, including some initial conditions, how do I investigate if a system is linear? Well, I can check the operations that are in use, which in this case are all linear operations, so the system could be linear. But a hardcore mathematical proof would stem from the definition of linearity. We have actually already done this in lecture 7, but in this lecture it bears repeating. If in the system described by this differential equation, an input u1 creates an output y1, then this relationship must hold. If an input u2 creates an output y2, then this relationship must hold. Now, should the system be linear, then the input given by this linear combination of these inputs must create the output given by the same linear combination of these outputs. So let's verify that. Substitute this input here and substitute this output here and here. The substitution gives this, which you can rearrange into this form where all y1s are grouped and y2s are grouped. Now, based on this equation, this must be equal to u1, and based on this equation, this must be equal to u2. Thus, the left-hand side is equal to the right-hand side and the system should be linear. Except, let's check this initial condition. This initial condition says that at time t0 the output should be y0. So at time t0 this output must be y0, this output must be y0, and this output must be y0. Now, if the linearity holds, this must hold, and it must hold even for the time t0. But at t0, this is equal to y0, and this is equal to this, which you can write like this. So this is supposed to be equal to this, and for general a and b, this will happen only if y0 is 0, that is, only if this initial condition is 0. Therefore, there is an additional requirement for linearity, and that is that the initial conditions are 0. If the initial conditions are not 0, strictly based on the definition of linearity, the system is not going to be linear. So, if you ever get bored, you can examine that equations like these with 0 initial conditions describe linear systems. Now, let's take a look at an example of a nonlinear system. Let's examine a system described by this equation. If an input u1 creates an output y1, then this relationship must hold. If an input u2 creates an output y2, then this relationship must hold. Now, if the system was linear, then the input given by this linear combination must create this output. So let's verify that. When I substitute into this equation, I get this. This right-hand side I can expand like this. Here I can substitute y1 and y2 for this and this, which will give me this. However, this is not equal to the left-hand side of the equation. Therefore, the system described by this equation is not linear. In fact, you can see it directly from this equation. This square is not a linear operation. So, this is how you formally investigate linearity of systems. Now let's take a look why do we care so much if something is linear or not. Basically, except for some work with non-zero initial conditions, or our previous work was with linear time invariant systems or LTI systems. Now for those linear time invariant systems, we developed a body of useful theory that allows us to examine and sometimes even build those LTI systems. We learned about things such as frequency characteristic, transfer functions, zeros, poles, and stability analysis. And all these things were derived only for the linear time invariant systems. Additionally, with linear time invariant systems, we had some nice behavior. When I feed an LTI system a cosine or a sine, the output is the same cosine or a sine except scaled in amplitude and shift in phase. When I feed an LTI system an exponential, the output is the same exponential except multiplied by a complex number given by the frequency characteristic at the frequency of the exponential. In fact, this can be generalized to a general complex exponential and a transfer function. And this is why we say that the complex exponential is the eigenfunction of the LTI system. When you feed a complex exponential to an LTI system, it is only multiplied by a complex number. Moreover, for an LTI system, the spectrum of the output can be easily computed from the input spectrum by just multiplying it with the frequency characteristic. And if you express your signal as the inverse Fourier transform of its spectrum, then the output can be easily expressed as the inverse Fourier transform of the spectrum of the input signal multiplied by the frequency characteristic. All of this theory is usable only for the LTI systems, and that is why we like them so much. Now, what about nonlinear or time-variant systems? Now, for these systems, there is no frequency characteristic, no transfer function. So all of that theory that we have learned thus far is pretty much unusable. Let's see what can happen with nonlinear systems. Here I have a very simple nonlinear system, and let's see what happens when I feed it this input. This will be the output, which using trigonometric identities you can rewrite like this. Here you can note that I have fed the system a cosine at the frequency omega, but the result is a constant and a cosine at a frequency 2 times omega. So you no longer have this relationship. A nonlinear system can take a cosine at one frequency and it can create signal that contains completely different frequencies. This is considerably more complex behavior than what we were used to with the LTI systems. Here I have another example to show you what can happen. This time I feed the system this sum of these two cosines at frequencies omega 1 and omega 2. The output of the system is this. When I expand this bracket, I get this, and when I use some trigonometric identities, I can actually write this expression like this. So from this input that contain frequencies omega 1 and omega 2, the system will create components at twice the frequency and at frequencies given by the difference and the sum of the original frequencies. So again, this is nothing like what we had with LTI systems. This is not necessarily bad. In fact, we can utilize this behavior, for example, in modulation and demodulation, where we need to shift low frequency signals to high frequencies and vice versa. But in any case, especially for more complex signals, this behavior is considerably more difficult to track. So what do we do when we encounter a nonlinear system? Well, we have two options. We either learn to live with the nonlinearity and sometimes even use it to our advantage, or, and that is what this lecture is about, sometimes we can try to approximate a nonlinear system with an LTI system, which would allow us to at least approximately apply all the theory we have learned so far. To show you how we can approximate a nonlinear system with a linear one, let me first show you a case where it simply cannot be done. As an example, I will use a diode. On a diode, the current and the voltage can be approximately described by this so-called Shockley equation. And I will consider this description as a system where the input is the voltage and the output is the current. These I sub s, n, and v sub t are just some constants. I sub s is so-called saturation current, v sub t is so-called thermal voltage, and this n is so-called ideality factor. Obviously, this is a nonlinear system. This exponential is definitely not a linear operation, and nor is this addition of a constant. Now let's examine what will be the output of the system when I feed it a sine function. First, this is the current voltage characteristic of this diode. It is basically only a plot of this function, and it tells me what will be the current for a given voltage. Using this current voltage characteristic, I can graphically examine what will be the output of the system when I know the input. Let's say the input is this sine function. This sine function is drawn on its side. On the vertical axis I have time, which is growing downwards, and on the horizontal axis I have the voltage. Now I can go point by point and I can find what are the current through the diode for the voltages in various times. So for example, at time 0 I have 0 voltage, which will create 0 current. So at time 0, the current will be 0. At time 1, I will have this voltage, which will create this current. So at time 1, I will have this current flowing through the diode. At time 2, I will have this voltage, which will create this much current. So at time 2, I will have this current flowing through the diode. At time 3, I have this voltage, which corresponds to this current through the diode. At time 4, the voltage is 0, and so will be the current. At time 5, I have this negative voltage, which will result in this small amount of negative current, so this will be the current at time 5. And in similar fashion, the voltages at times 6 and 7 will create currents at times 6 and 7. If you did this process for every value of the input voltage, you would get this curve, which would be the time course of the current through the diode. Here you can see that this behavior is nothing like what we had with the LTI systems. An LTI system with a sine function at its input would give you the same function at its output except scaled in amplitude and shifted in phase. Here, the top half of the sine is distorted and the bottom half is cut off, which is nice when you want to use the diode as a rectifier, but you cannot use the theory we had for the LTI systems to describe this behavior. In fact, in the case of this input signal, the behavior of the system is so different from the behavior of an LTI system that we cannot do anything about it. For this signal, our system is not behaving like an LTI system, not even approximately. This behavior we call the large signal behavior, and why it is called the large signal behavior you will see when we talk about the small signal behavior on the next slide. So on this slide I have the same diode, the same system, but this time I will feed the system a sine which is much smaller in amplitude, and I have also added some non-zero constant value, some DC bias. So my voltage, my input signal, can be expressed as some constant, which is that DC bias, plus some small change that will be added to this constant. In this example, the small change is a sine with some small amplitude. Specifically, here I'm using a DC bias of 70 millivolts and the amplitude of the sine is 10 millivolts. Now let's see what will be the output for this input. When I use the same graphical method for finding the current created by this voltage, I will get the current indicated by this blue line. This voltage will create this current. This voltage will create this current. This voltage will create this current, and so on and so forth. Now, when I consider this to be the input to my system and this to be the output, I can see that the behavior of the system is getting a bit closer to what we saw with LTI systems. The output is not exactly a sine wave, but it is quite close. At least much closer than what we had on the previous slide. So the current, that is the output of my system, I could approximate as some constant, that is some DC bias at the output, plus some change added to that DC bias. And in this example, I can approximate the output as a constant plus a sine function. This sine function is obviously going to have a different amplitude than is the amplitude of the sine function at the input. The amplitude of this sine is different from the amplitude of this approximate sine. Now, if I decide to use this approximation, how can I find this I0 and this B? Well, I0 is easy. V0 is the DC bias at the input, that is this voltage. I0 is the DC bias at the output, that is this current. And what is the relationship between this voltage and this current? This equation says the relationship. When I substitute V0 here, I will get my I0. Actually, this V0 and I0 are coordinates of this point, and we refer to this point as the operating point. We say that this V0 and I0 constitute the operating point. Now, what about this amplitude? To find this amplitude, I will approximate this current voltage characteristic of my diode with a straight line that is tangent to the current voltage characteristic, ideally somewhere in the middle of the range of my input. In the middle is the operating point, so I will make this straight line tangent to the current voltage characteristic at the operating point. This red line will have this equation where this k is a constant that will determine the slope of this red line, and this delta V is this deviation of the voltage from the input DC bias. It is this delta V, which in my example is this sine. To make this red line tangent to the current voltage characteristic, I have to make its slope equal to the derivative of the current voltage characteristic at this point. So this is how I have to compute the constant k. Now, if instead of this curved current voltage characteristic I use this straight line, the output will be this red curve. Mathematically, this delta v, this delta v, this delta v gets multiplied by this k, which will give me this red curve that corresponds to this sine. So the amplitude of this sine will be the original amplitude multiplied by this k. To write the relationship between the input and the approximated output in a more convenient way, I can take this equation here, put this term to the left-hand side, which will give me this. This is the difference between the diode current and the DC current at the operating point. That corresponds to this delta I, so I will denote it as delta I. Subsequently, I can write this equation, which is an approximate relationship between the change of the voltage and the change of the current. This change of input voltage around the DC value constituting the operating point, and this change of current around the DC value constituting the operating point. Note that this relationship is linear, so when this delta V, this change around the operating point, is at the input of my system, I can approximately find what is the delta I, this change around the operating point at the output of my system, using a description with a linear system which I know how to deal with. The precision of this approximation will depend on how well this straight line approximates the true current voltage characteristic of the system. If I'm very close to the operating point, the approximation will often be good. If I'm far away from the operating point, the approximation will be quite bad. Now, if my input values are close to the operating point, that is, this delta V is small, the approximation by the linear system will be good. This behavior we refer to as the small signal behavior. For the small signal behavior, where my signals manifest only small changes from the operating point, I can approximate this curve with a straight line, so at least for the changes in the close vicinity of the operating point, the nonlinear system can be approximated by a linear one. This is in contrast with the large signal behavior, where this approximation was not possible. There is no exact limit that tells you what is small and what is large signal behavior. It depends on you and your application that will dictate how much deviation you are able to accept. For example, in this case, if I wanted to approximate the output signal and I can tolerate these errors, then I'm okay with treating this as a small signal behavior, which allows me to use this approximation. However, if these errors are unacceptable, I cannot make this approximation. I cannot treat this problem as a small signal behavior. I have to approach it as the large signal behavior, take the nonlinearity fully into account, and suffer for it. The process of approximating a nonlinear system with a linear one is called the linearization. So on this slide, I showed you a minimalistic example of linearization. On this slide and on the next slide, I will make the linearization a little bit more general. If my system is described by an equation in this form, then mathematically I can approximate this function f around some point u0 by its Taylor series. The Taylor series is given as the value of the function f at the point u0, the first derivative of the function f at the point u0 times the deviation of the input from the point u0 plus some higher order terms that contain higher derivatives of function f. Now we can neglect all these higher order terms and keep only this constant term and this first order term. Here this u0 and the value of f at u0, that is this y0, will constitute my operating point. Then I denote this derivative as k and this deviation from the operating point as delta u. That will give me this equation, which is the same equation that we used for the approximating line on the previous slide. So this is how you derive it more formally using the Taylor series expansion. And as on the previous slide, I can move this y naught to the left and denote this difference as delta y, which will be a change, ideally a small one, of my output signal around the operating point given by the second coordinate y naught. So I can describe the relationship between the change around the operating point at the input and the change around the operating point at the output using this linear equation where this k is equal to the derivative of this function at the operating point. Again, for this operating point, I can linearize this nonlinear system and use this linear approximation for small changes at the input and at the output of the system. This approach is still rather limited to a case where the output is just a nonlinear function of the input. On the next slide, we will take a look at how we can deal with an even more general case. If you need to linearize a system described with derivatives, you can convert it into the state space representation and perform the linearization there. Specifically, you can do it like this. This is a general state space representation where the change, the derivative of the state vector, is given as a general function of the state vector and the input, and the output is given as a general function of the state vector and the input. I will show you the linearization for the case where we have a single input, single output, and the system has the second order. That is, it has two state variables. In this case, this vector form of the state space representation can be expanded into this scalar form where these f1, f2, and g are some general functions. Now the linearization is done in two steps. First, we need to determine the operating point, and then we need to perform the linearization around that operating point. First, the operating point. As an operating point, we need to pick the state where the system can remain steady by itself and it does not have a tendency to run away from that state. I will demonstrate this idea on a pendulum. The pendulum can be described by two state variables, its angle and angular velocity. Additionally, in this explanation, I will assume that the external forces acting on the pendulum do not have some non-zero average component that would constantly push the pendulum to one side. Now, imagine that you want to linearize the motion of the pendulum for small deviations around an operating point. You can pick your operating point as a state with zero angle and zero angular velocity, that is the state in which pendulum is here and is not moving. The pendulum can either remain steadily in this state or we can make it move in the close vicinity of this state. When this happens, the linearization can actually be quite good and usable. However, what you cannot do is to pick the operating point as a state for which the angle of the pendulum would put it, for example, here. It doesn't even matter what the angular velocity would be. You cannot expect the pendulum to remain in the close vicinity of this position. Even if you moved your pendulum to this position at some initial time, the pendulum would immediately leave this initial position. Unless there would be some continuous force pushing it sideways, there is just no way the pendulum is going to steadily remain in a state that would keep it at this place or in its close vicinity. Consequently, if you picked this position for your operating point, the movement of the pendulum would not be just some small shifts around the operating point. Therefore, the movement of the pendulum would correspond to the large signal behavior, and any linearization around an operating point corresponding to this position would be quite imprecise and most likely unusable. So, it is best to pick the operating point at the state where the system can remain steady and it does not have a tendency to run away from this state. Then, when we introduce some small changes to the input of the system will transform them to some small changes at the output. And such behavior we could try to approximate by a linear system. Now, how do I express this steady point mathematically? It's actually quite simple. I'm looking for a state in which the system will remain steady. That is, in mathematical language, I'm looking for a state in which the derivative of the state is zero. This means that I'm looking for the values of the state variables for which the derivatives of the state variables are zero. The part of the operating point given by the DC bias at the input, that is this U0, is typically set by the designer. It is typically given. So to find a suitable operating point, I need to find only these two remaining coordinates by solving these nonlinear equations. When I find the operating point, I can start with the actual linearization. This again will be based on the Taylor series. This function f1 I can approximate by this Taylor series. The constant term will be given as the value of the function f1 at the operating point. The first order term will be given as the derivative of the f1 with respect to x1 at the operating point times the deviation of x1 from the respective coordinate of the operating point, plus the derivative of f1 with respect to x2 at the operating point times the deviation of x2 from the respective coordinate of the operating point, plus the derivative of f1 with respect to u at the operating point times the deviation of u from the respective coordinate of the operating point. The Taylor series can have higher order terms, but those we neglect and we use only this approximation. Just a small note, these state variables and this input are all functions of time, but to reduce the clutter I have dropped that argument of time from these equations. Now I need to realize that we have chosen the operating point so that this is 0. So this goes away. Then I can denote this as delta x1, this as delta x2, and this as delta u. These deltas correspond to small variations around the operating point. And also I can write the derivative of the first state variable like this, because the derivative of this constant is 0. Now I can denote this as derivative of some delta x1. When I do this, I can write this equation like this. And this would be the linearization of the first state equation. The second state equation I can linearize in the same fashion, which will give me this. And the output equation I can also linearize in the same fashion, which will give me this. Here I have a small difference because this function is not 0 at the operating point. The value of this function will in fact give me the part of the operating point at the output, which I will denote as y0. This y0 I will put to the left hand side, and on the left hand side I will denote this difference as delta y, which will correspond to some small deviation around the operating point at the output. At the end, this will be my linearized state equations, and this will be my linearized output equation. If you wanted to put this state space description into the matrix form, for example to find a transfer function of the linearized system, you can write it like this.